Okay, so my plan for today is to briefly discuss this article and also take a look at the end of the chapter 15 and afterwards talk about 19.4 in details. Uh, yeah, okay, so let's start with that paper. So basically that paper kind of uses the uh, economical model to demonstrate what gauge symmetry means actually, and it was really enlightening for me to read that. So it basically discusses symmetries here in the second section. Talks about like global versus local symmetries, and we can see here like a global symmetry where the whole system was rotated, and when you are located like uh, here like inside the ship, uh, you cannot tell if anything changed when the whole system been rotated. So yeah, and on that picture you can see that if you rotate a cup inside the ship or a bucket, then you will obviously notice that. So you don't have like a local symmetries there by rotating a bucket. Yeah, and afterwards it discusses like active and passive transformations and also divides like symmetries and redundancies. Uh, and like the basic idea here is that like passive transformations, they just kind of change our coordinate system and doesn't change anything physically. And active transformation uh, active transformations are more connected with like a physical world impact, and therefore we can say that symmetries should be like active ones, and they should be connected to the real world, and the one symmetries which are called here redundancies, they are more connected with the passive transformations, uh, and basically they are just like renaming our coordinates or entities inside the system, but doesn't um, change. They don't change anything in the essence, basically.
And that's just the coordinate transformations that we talked about earlier, right?
Yeah, something like that. So it could be like a coordinate transformation, but or maybe some other transformation which like doesn't change anything in the reality. So it kind of just a matter of the notation, and coordinate transformation is just like one of the examples. We will see more examples later when we will see the gauge transformations, like in quantum mechanical systems, for example, where we will use some kind of the complex rotation, right? So we like don't change the coordinates, we change something in the system, but anyway, it is not like measurable in the real world. So we will talk about that a bit later. But anyway, you just need to grasp like that division between active passive and symmetries versus redundancies, and that's enough. Yeah, so and in the chapter 3 here, author begin to talk about the economical toy model, like a small financial market example, and he talks about like, for example, we can have something like Europe, a few countries inside like Germany, France, United Kingdom, and Italy, and we can have like a global currency inside like euro, and for that currency we will have a global gauge symmetry, and that means that we can shift the currency or alternatively all prices without any physical effect on the whole system, like in the real world. And that's actually kind of the passive transformations, it seemed to me, because like in the real world, it will not change anything. So it's just the matter of like numbers on your papers with which you pay for the products, right? So when you shift everything relative to everything, you will still be able to buy, for example, like exchange three tomatoes for like 6 apples, like on the picture, on the pictures below. So it doesn't matter how much it will cost if all the relative prices will change. And that thing is called like a global gauge symmetry. And instead of doing that, we can also consider the local currencies. Like in Germany, we have Deutschmarks, in France we have francs, and in England we have pounds, and in Italy we have liras. So basically, we can introduce like the bookkeepers, the exchange rates between countries, and therefore we will obtain something like that, like the situation depicted on that figure, which you can see on the screen. So we kind of can exchange Deutschmarks for the pounds and pounds for francs, and just make like a travel between the countries using our like currencies. And now we can see that if, for example, one of the governments decides to drop like a zero, for example, from their currency, so basically change the value of their local currency, the bookkeepers will guarantee for the whole system that that local change will not have the impact on the like Europe overall. So basically you will have like different exchange rates, but the whole how to say, like the buying power of the currency will not change. So basically, if you will try to exchange one Denmark and exchange that in the same sequence as before, you will still will have the same one Deutsche Mark at the end. So basically, that means that local rescaling makes no difference as long as the exchange rates get adjusted accordingly. Yeah, and as far as I remember, somewhere here, like in that paragraph, he talks about that, like those bookkeepers, they are actually not so like needed in the case when we have no arbitrage opportunities. So basically, where our like those exchange loop provide no like net profit or loss for us. Yeah, and basically it means that it's kind of a redundancy symmetry here. But when those like exchange rates become like a real, what he calls like real dynamic entities on the market, which will kind of have their dynamics and they will impact prices, and prices on the like tomatoes will impact those exchange rates, then those like bookkeepers become something like real and not just a redundancy. Yes, so in chapter 4 he introduces like the notion of arbitrage opportunity, and basically it arises when like some bookkeepers maybe like from some, I don't know, some because of some economic reasons they kind of fluctuated maybe, or like are not fair in some sense, and basically therefore you can kind of make net profit on your exchanges. and for example we stood Deutsche Marks at the end here, and probably maybe even before, but at that place it could remind you about the curvature, which we have seen in the Penrose book and maybe in other books, in gravity theory, right? So basically it's just like some kind of the curvature here. So we have a loop, we transport something over the loop, and we have the changed quantity. So that arbitrage opportunity means that we have non-zero curvature in our system. Yeah, and afterwards he just explains that, like, mathematically, I think that we can skip that. So if you're interested, just read that in detail. But the interesting moment here is that by like from that mathematical description we can obtain really familiar notions like electromagnetic potential or Maxwell Tensor here, and basically those will describe, that will describe the curvature, the arbitrage possibilities in our system, and those A's here, they will describe like some kind of the logarithm exchange rate. I don't remember exactly. Yeah, so if you have like exchange rates described by R, then our A's here are just logarithms of the R's. Yeah, so basically it's like logarithmic exchange rates, and F will be our curvature. And the interesting moment here is that if you have some kind of the good, like a copper, for example, and we have some kind of prices, like local prices in different countries on the copper, and we can also like make different exchanges of our goods between countries, and those prices on the goods, they will kind of induce some analogy to the currents in the economics. So basically you can see that we will obtain some kind of the J here, which kind of reminds us about the currents from the electromagnetic theory. And afterwards, by considering that the copper is conserved in our system, the same as the charge, right? Or like charge current conservation, you will be able to derive something similar and familiar to the Maxwell equation, like that. So it's kind of enlightening that electromagnetic theory has such a representation in economics. Yeah. But anyway, if we'll go back to the physics now and take a look at the gauge symmetry in physics, then basically like we have like two different two main domains, like quantum mechanics, right, and electromagnetics. So in this section 5 of the article, Jacob talks about like gauge symmetry in quantum mechanics, and afterwards gauge symmetry in electromagnetics, and afterwards talks about how do we combine those. So they're kind of connected between themselves. And he talks here that like in our money toy model, we use the local prices to describe traders carrying goods like copper around. And by the same analogy, in quantum mechanics, we use the wave function to describe particles carrying electric charge, like for example electrons. So basically, like wave function is like a trading agent, and charge is like a copper also. So And in that case, we can describe those wave functions in a polar form, where we have like two functions. One is r of x, and another one is like phi of x here, and with corresponding exponential, complex exponential here. And we will see later that, like in quantum mechanics, usually we will have also like a dual wave function to the original one, and usually in our calculations we will need to kind of multiply those with some kind of the matrix or operator called observable, and obtain some kind of the number, like a probability for some event here. But like basically that means like that multiplication of psi and psi star here, it means that if we will rotate complexly rotate our wave function with some fixed constant epsilon there, then that effect will not be observable basically, and because those exponentials, they will just cancel out, and you will have as a result the same expression here. And in the article it's described as a global symmetry. So basically, if we will change our wave functions externally here by some phase transition mechanism, then the physician inside the board, he will not be able to determine if that phase shift has been done. Yeah, and therefore we have that like global gauge symmetry in quantum mechanics. And we can ask about like a local phase shifts now. And locality means that instead of having a constant here, we will have like epsilon of x, some kind of function, which will depend on our space-time or space coordinate like x here. So in that case, we can consider, for example, like a momentum operator here, and momentum operator equals I minus dx here. And because of the derivative there, you can notice that we will obtain, after substitution of our new wave function into the equation, we will obtain one more the additional element here, which will be equal to that dx from epsilon x here, and therefore it will not be equal to the p hat of our original wave function. But we can fix that situation by modifying our observable a bit and creating what is called covariant momentum operator, and we can add there some function of x, like ax here, and we can transform that bookkeeper.
Slava, can I please ask you can you zoom in a little? It's a little hard to see on mobile, the characters, if it's possible.
Yeah, one moment. Of course. Is it better?
Much better.
Right. So basically we are modifying that p hat operator, which was just minus I dx there, and we add in a small addition, that function a of x, and when we will transform our system, when we will apply the exponential rotation to our wave function here, we should modify our bookkeeper in that way. So basically that transformation will go in pair with the transformation of the wave function. And because of that, we can see that for the new p hat, p capital hat operator, we will have that equation, and at the end you can see that uh, like that one dx of epsilon and the dx of epsilon coming from the derivative operator, they will cancel out, and therefore we will obtain the same like covariant preserved notion for the like observability of our wave function. So physically nothing will change. Yeah, but now he asks that like, but are those local phase shifts a real symmetry of quantum mechanics or not? And to understand this, we should use also the same analogy, like the real world analogy of the physicist in the boat. And basically, like in that like first situation on the left, you can see that we have like non-modified wave function, and we have some like we perform the double slit experiment in which we have like interference pattern on the screen here, and on the picture at the right we see that we have some kind of the mechanism which will shift the phase of our wave packets, and therefore we will have a differing interference picture on the screen here, and therefore it will be observable for the physician, and because of that we can conclude that the local phase shifts are not symmetries of the quantum mechanics, because like the real situation will be like if you will change those, then that will be detectable by the physician. Okay.
Does that mean it's not global, or what?
Yeah, I'm now thinking about that also, like so he just says here, as far as I understand, that those like bookkeepers, they are not like real dynamical actors. Yeah. So as far as
I think it's that.
Yes.
I think it's that now we're just using them as a mathematical tool to impose this symmetry, and it's possible that this mathematical tool might have some physical significance.
Yeah, that's what I understand I was saying also, but I don't think this is the question here.
Yeah, so the question here is like, are those local phase shifts a real symmetry in quantum mechanics? And basically, like, we have a local phase shift here done, right? And we don't have a symmetry because like we are seeing the different interference pattern on the screen. Yeah. Okay. I think I got it. So basically, if we will change, like shift, make a phase shift here, the difference will be observable, right? But we know what we should do to cancel those. So basically, you can change your potential, like those A's, and basically negate the impact of that mechanism which applies the phase shift to the screen. So it's kind of not real symmetry because like we can just compensate, and like the yeah, so I'm not sure that I'm understanding that right here, but I think that it is like a right direction here. So basically it's not a symmetry because by having that mechanism, like phase shifter here, the result will change. Yep. And like those bookkeepers, he says that those bookkeepers are not real dynamical actors. Okay, let's just jump to the electrodynamics and see the situations there. Maybe afterwards we will be able to tell more about the situation in quantum mechanics. So it's kind of hard for me to formulate that at the moment. Okay, so in electrodynamics we have like Maxwell equations, and we have electromagnetic potential there, and we can add arbitrary real numbers to it, or like any gradient of any function, like the whole gradient here, but real numbers are perfectly good to be added there, and therefore, yeah, so, and this comes about because we can only measure potential differences, okay, and now we can test like the same thing. First of all, like the global symmetries. So we can try and to change externally the potential inside the ship. So you can see it here. So if we will change the whole like potential for the whole ship, the physicists inside the ship would not be able to detect that shift in the potential, and therefore we have that like a globally gauge symmetry for the electromagnetic potential.
Is this, I mean, I thought the ship represented the local. I thought it would only be changing locally, and that is only the case that it can't detect the global scale. I mean, it's only measuring it on the local scale. How can he tell that it's...
No.
I guess he can't tell the difference.
Like the situation with the ship is kind of like think about that like in the Galilean experiment, right, where you was in the ship,
yeah,
and everything is moving uniformly. You cannot detect if ship is moving, right?
Yeah, I don't know.
And that's the same thing here. So basically you change the outer, like the state of the ship from the outer world, right? So you kind of make its like charge bigger basically in comparison to the outer world, but inside you will not be able to measure that. And
well, right. I think it seems it only changes locally.
Well, I think that local and global are defined in terms of the light there, like the wave function that describes his laser or whatever that is. Because in the last figure where we had the phase shifter on the other side of the screen, if it covered both slits on that screen, that would still be a global transformation. But if it only partially covered one of the slits, then it would be local.
Yeah, and you can see here in the article that he says like globally inside the ship.
That does clarify.
So it means that he considers like the whole world as we are inside of like the very big ship.
Okay.
Yeah, so it's basically global system, the whole isolated system. Yeah, and if you try to make like a local change here, you can put some kind of a solenoid here, and you will be able to see the difference in the double slit experiment. And that's basically the Aronoff-Bohm effect, where non-zero potential induces a phase shift in the wave function. And he says here that the most important point is that in electrodynamics, our bookkeepers are dynamical physical actors that can induce real physical changes. And that's exactly like the phenomenon which is described by Aharonov-Bohm effect. And he sees that he says that we can define the quantity like that Maxwell like Maxwell Tensor, right? And that will encode the in the gauge invariant terms information about the presence of electromagnetic fields. Yeah. So, and here he says also that a local shift of the electromagnetic potential is not symmetry of the system. Okay, and he says that, so it's kind of situation is really like repeating itself in that case, right? Because we can detect the local change in the like phase shift here. Okay,
well,
so
and here the closed path is around the solenoid.
yeah.
I think this this curvature that we get is when you walk a path around the solenoid.
Yeah, of course, yeah. So, like, he says here that, like, we will have like a zero field around the solenoid, but we will have like a non-zero potential, and that non-zero potential will induce a phase shift in our wave function here, right?
Yeah, and it's related to we don't have to go too far into this, but it's related to like a contour integral, where like if you were to like integrate over the path that loops around the solenoid, you'd have a pole, and the residue that you would get from that integral actually would be related to that phase shift.
Yes, yeah. That's actually discussed in the Penrose book. We'll see the like we'll talk about that today also. But anyway, let's go further to the 5.3 here to put everything together. So basically we have seen that we have global symmetry in quantum mechanics, but not a local one. So basically we can use that complex rotation with the constant, but not with the function. And we then learned that we can rewrite our equations such that they are invariant under local transformations by introducing bookkeepers, those like potentials. And afterwards we argued that the invariance under global transformations represents a real symmetry, while the invariance under local transformation is only a redundancy. Formulated differently, we have invariance under active global transformations and passive local transformations if you write the theory appropriately. Yeah, give me a moment just to read that. Yeah, so basically here he talks about that like our bookkeepers become real in electrodynamics because of the Aharonov-Bohm effect. Okay, and what this implies immediately is that in principle it's possible to cancel any local phase shift using an electromagnetic potential. However, it's important to take note that we still do not have a local symmetry when electromagnetic potential is present, for example in the ship in which our quantum physics detects local phase shifts. Okay, so it's instructive to reformulate this point using the notions of active transformation and passive transformation. And a passive transformation is simply a change of the coordinate systems, and therefore cannot lead to any physical change. All we achieve through a passive transformation is a different description of the same physical situation. And therefore, when we perform a passive transformation, we must be careful to keep our description consistent. This means in particular that whenever we perform a local passive transformation, we have to accompany the change of the wave function with the change of our bookkeeper here. When we perform a passive transformation, these two transformations always go hand in hand. And in contrast, an active transformation means that a real physical change happens, and therefore the physical situation doesn't need to remain unchanged. In particular, when we induce an active local phase shift like that, the corresponding transformation of a mu does not happen automatically. Otherwise, we wouldn't be able to detect local phase shifts in experiments. Yeah. So, okay. So basically it means, probably he will summarize it here, that like quantum mechanics and electrodynamics are invariant under active global gauge transformations. And hence global gauge symmetry is a real symmetry. However, only our description is invariant under passive local transformations. Therefore, local gauge symmetry is just a redundancy. So basically we can change we can passively transform our notation locally by using the pair of those formulas, and that will not imply the change in the real system, like the real physical change. But in a real physical system, we can also induce a local phase shift, and we can cancel that out by using change in our electromagnetic potential, using a solenoid, for example, and applying Aronoff bomb setup to our system. And in other words, those two active shifts will be two separate transformations which can happen independently. So as far as I have understand that, he just wanted to make a really clear distinction between local and global gauge symmetries here, and to tell us that yes, global gauge symmetry is the real one, and it's not measurable, right? So we cannot measure it, as far as I understand that. But local one, we can measure it, and by applying those local changes, we can kind of first of all we can see different interference patterns, for example, in the experiments, and we can also see the reality of the electromagnetic potential in our experiments. Okay, so yeah, it seems that's all for that paper for today, because afterwards he will just talk more about mathematical descriptions, a little bit more about connections. So he will say that those bookkeepers are actually called connections, and those are connected with parallel transporting something, some values or vectors. And we'll have our Maxwell Tensor at the curvature of the connection there. So Any questions about?
Yes. I almost forgot. What is global symmetry? It seems to me that we have to be able to indirectly infer this somehow. Otherwise, we would not even consider that there is something such as global symmetry. I'm saying that it has to be observable indirectly in some way.
Well, I think the way that it's indirectly observable is just showing that that charge is also locally conserved. Meaning, like, he wrote a continuity equation toward the top of the paper, and that continuity equation basically it just tells you if you want to observe a change in charge density, it's going to change due to currents flowing. And that's what that continuity equation tells you. And you can derive a continuity equation from this global symmetry. And so as long as you can observe that charges don't just disappear and appear somewhere else, as long as you can observe that they actually flow in currents, then you are observing this global symmetry indirectly.
This makes me think of what is it, Noether's theorem, which is about the conservation of energy. I'm thinking.
Yes, that's exactly right. So the conserved quantity is what's called the Noether current, and the continuity equation that's written down in this paper is for the Noether charge current.
Mm-hmm. Yeah, we'll talk about the Noether theorem in the chapter 20 actually. Yeah, but anyway, I just scrolled up to the definition of the global transformation, and he talks about the global transformation of a subsystem, say a ship, and global means that the whole ship is rotated and not just some part of it. So
that's clearer.
Yeah, so it's just about global in terms of the subsystem.
So it's a change that does not change relatively to itself.
Yeah. So if you are a part of that subsystem, you will not be able to detect that. But if you will go out, if you look outside, right, then you will be able to detect that.
Right. So you could this global transformation could be of as you say, of a subsystem. So it could be on any scale, an arbitrary scale.
Yeah. Okay, so just to summarize, basically that paper, first of all, it gives that really interesting metaphor from the economy theory, and also talks a little bit more about those how to say that differences between global versus local, or active versus passive, and also symmetry versus redundancy. So those points were really important, I think. Yeah, so let's switch to the book and take a look at the chapter 15. So I just want to go through that in a really fast pace. So basically in 15.7 we have introduced what is called non-triviality in the bundle connection, and the basic idea here was first of all to transfer the notion of the connection from the manifold to the fiber bundle. And in the manifold we have had the tangent spaces at every point of the manifold, and we've been able to push or parallel transport the tangent vectors on the manifold from one tangent space to another one, and that that was like the meaning of the connections there. And by using the same metaphor, on the fiber bundles, we have like a base space here, M, and we have a fiber at the, like above every point of the M. We have the fiber bundle here, and therefore connection will kind of propel or like push the values from one fiber to another. So it just basically means to connect or glue between the fibers. So how we associate one fiber with the neighboring fibers. And like that's the basic idea. And the connection kind of corresponds to the constancy or horizontality in the fiber bundle here. Yeah, and therefore we have here the example of a cylinder. So we have just S1, a circle as a base here, and a line as a fiber, and we have non-triviality in that fiber bundle by using the stretch transformation. So we stretch our lines there. So after like going the full circle in our bundle, we will have like a doubled value here. So if you started with 1, then you will end with 2 here. So, and it's basically like smoothly smoothly divided.
Gradual rise or something.
Yeah, so you will have some kind of like a spiral rise around the cylinder while traveling between the fibers. And that's exactly like the non-triviality in the connection, because like for the trivial connection you will just slice a perfect circle here and you will end at the same point. But in this example you will have a path dependence. So if you go from A to B here, you will go like down, and if you go from A to B like following the white arrow here, you will go up, for example, and you will end like further on the spiral. And like it's interesting that it has some connection with what is called like Penrose Stairs. Maybe you have seen those somewhere. I don't know.
I was gonna mention that before. Yeah, interesting.
Yeah, and Escher, if you heard about him, like he was a Dutch artist. He'd been using those in pictures. So basically, you can see the kind of those stairs here, and it's kind of reminds me about that example from the Penrose book. So that's exactly the non-triviality in the connection of the fibers. So those people can descend and ascend infinitely on the picture, and it seems that those like paradoxical stairs, they can lead you on this like infinity spirals, basically. Yeah. So, and those Penrose Stairs, they have like pretty interesting history because they made popular by Penrose's father Lionel and himself, but they were created by Oscar Reuterswart probably like 20 years before them, and actually Escher was inspired by the Penrose, and basically he used, as far as I have understood, he used the Penrose Stairs in his pictures after the Penrose wrote a letter to him, as far as I understand that.
I think he was Swedish, if I remember correctly, and it's pronounced. His name is pronounced like Oscar Reuterswärd.
Reuterswärd.
Not that it matters.
Yeah.
Reuterswärd. Yes. Kind of.
Yes, Swedish graphic
Just
artist.
trivia.
Yeah, and also you can see that we have something similar in music called like Shepard Tone, So it's like a tone used, like which is like seems to our ear always like moving upward or downward, and it's also really interesting. You can listen to that on the YouTube somewhere.
Yeah.
So
it seems to rise and rise and rise infinitely, even though you keep repeating, even though you can't really tell, because relatively speaking, it's increasing to the step before, and somehow your mind doesn't grasp the whole.
Yeah, so basically you kind of travel in this spiral here, and all of those, they're kind of the good examples of that fiber bundle which we have on the screen currently. Okay, so and afterwards, at the end of that section, he said that if you want to obtain something like a curvature and like not a global path dependence but a local path dependence, we should have like more dimensional base space. So and the example in 15.7 is really interesting because it has like it shows that it's possible to have path dependence globally even when there is none present locally. Okay, and in the next section basically we just substitute the base space, and like instead of having just a circle we take the whole complex plane. Fiber is the same, and afterwards we introduce the connection there. So like basically the cross sections of that bundle will be just real valued complex functions like phi here. And he says that when we introduce strain into the bundle connection, we can do this by modifying the operator d by dz to become the new operator delta or d del, like d by dz minus a, and you can see the same scheme we have seen in the finance toy model in the article before, right? So we kind of add in the bookkeeper here, and that will kind of guarantee the ascending or descending while moving between fibers. So basically I'm thinking about that in the way like derivative means like measuring something in the neighborhood, and basically you kind of, while moving from fiber to fiber, you kind of using the derivative. So I'm kind of metaphorically think about that in this way. So and that a here, it will provide some like shift in the fiber, and basically it kind of guarantees that we will move up or down while realizing that connection formula here. Yeah, so basically he also talks here about the curvature. So it's the same formula we have had in the chapter 14, but with complex conjugation, so it's like a complex curvature here. And he also says that we can like make a specific choice of A for which this commutator, the curvature, takes a constant non-zero value, and for suitable real constant k, we can get a stretching factor when we travel around a closed loop that is simply proportional to the area of the loop. So, and you can Google for that exercise 15.14 and take a look how to deduce that k and what the function should be to obtain the factor of 2 here. Yeah, so, and we have a picture here depicting what curvature means in that case. So basically it means that if you have in the base space some parallelogram, then that parallelogram will fail to close in the bundle. So basically that's what the curvature measures. So like how much those points will differ here. Yeah, and afterwards he also talks about that like in general we will have like more dimensional fibers, not like one dimensional there, right? And we can have like tensors there, so, and therefore he been talking about some tensor quantities instead just of the A with one index here. Yeah, but anyway, he been talking also here about that we can also generalize the situation or example by making our fibers two-dimensional by introducing the planes here and applying a real stretch factor to those. We could also interpret those as a complex one-dimensional vector space with a real stretch factor. And in the same way, we can go further and talk about complex stretching factors. And for example, as a part of the scheme, the complex rotations also. And in that case, you will obtain something like that, right? So it's just a complex planes with a rotation. And that's exactly what we will see like in the chapter 19. And that's exactly the situation which will happen with electromagnetism. We will have those like circles in the space.
Does this have anything to do with polarization, like circular polarization?
I don't know. I don't know. I think that it will be more suitable to talk about polarization when we will come to the like later chapters, like 21, when we will talk about quantum mechanics more, because I think that the questions of polarization, they will be more connected like with the wave functions.
I still think it's good to ask these questions, but yeah, you're probably right that we will see more answers to this there.
Yeah, because like currently, like I'm not exactly aware about polarization. So basically, as far as I understand it, it's just like the orientation of the electromagnetic wave. So basically, it seems like polarization is exactly the thing we are talking about here, like the phase factor. But like it's the real rotation, you know, not the complex one, and that's like the difference, it seems to me.
True. Not exactly so.
Mm-hmm. Okay, so that was like a small reminder about the bundle curvatures and connections in the bundle. And now let's go to the chapter 19 and at last talk about the gauge theory and electromagnetism. Somewhere here. Okay, so this section called like the Maxwell field as gauge curvature, and basically tells us that like the first Maxwell equation, which tells that we have a closed two-form F here, has the implication that there should exist some one form A, that F equals to the exterior derivative of that form, basically, and this is the like the result of the Poincare lemma applied here, and that quantity is called the electromagnetic potential, and it is not uniquely determined by the field F, but is fixed to within the addition of the some exterior derivative, or like a full gradient of some quantity theta here, where theta is some real scalar field, so it's basically just a gradient here. Okay, and therefore, one moment. Yeah. Therefore, that electromagnetic potential, it has some like standing out properties, and first one is that it is not locally measurable quantity. So there can be no experiment to measure the value of A, and therefore we can only measure the differences of that potential. However, that potential provides the mathematical key to the procedure where Maxwell field interacts with the wave function. And it works by using the gauge connection or bundle connection, which is defined by that equation. So basically we have the derivative here or gradient, and we are shifting like every part of it by the AA here, and that constant E here is a particular real number which quantifies the electric charge in that case. Okay, and in the next few paragraphs, Penrose talks about the the wave function. That wave function, we should think about that as the cross section of a bundle, and that bundle describing charged fields, and it is this bundle in which our connection defined above acts. And he also talks about the fact that the actual electromagnetic field quantities like F and A, they are uncharged, and basically the charge for them equals to 0. And therefore all of our Maxwell equations are undisturbed and preserved even in the curved spacetime. And afterwards he talks about the geometrical nature of that bundle in which our wave functions lives. And he says that one possible viewpoint is to think of this bundle as having fibers that are circles over the space-time, where this circle describes a phase multiplier for the wave function. And afterwards he also adds that it's more appropriate to think about that bundle as a vector bundle of the possible values for our wave function at each point. So basically we have like a curved space-time, for example, as a base space, and in the fiber we have like a product of some vector space which defines the values for the wave function, and also a circle attached, so which will determine the phase multiplication there. And therefore we will obtain like a separate like U1 bundle over the space-time for the phase of the wave function. Okay, and yeah, and he says that for that to make sense, we need to say that like our wave functions, they should be insensitive to the replacement, which equals like the multiplication by the phase factor here. Yeah, and this replacement is referred to as electromagnetic gauge transformation, and the fact that physical interpretation is insensitive to this replacement is called gauge invariance, and we have called that replacement global gauge symmetry in our previous article by Jacob. Okay, so, and the curvature of that bundle connection then turns out to be the Maxwell field tensor. So that's like the basic scheme. And afterwards, Penrose talks about the history. So basically, I see that as a, like, first of all, it's always good to know some history, right? But for me personally, it was really interesting
to keep it now in time.
Yeah. It was also really interesting to know from where the term gauge came out, because it wasn't like it wasn't it doesn't seem to me to be connected like with the things described by the gauge things. So basically here he talks about the story of the Hermann Weyl, the mathematician, and basically he has done a lot of different things, but one particular thing is he tried to make like the unification of electromagnetism and general relativity in 1918, and in that generalization he tried to like go further out of the Riemannian geometry and to make a more general geometry by forcing it to have like a metric only up to proportionality. So basically he allowed the transformations j to lambda j, and here we could think about like those rescalements like by some scalar function lambda as changing our gauges. So basically gauges is just like measurements or like I don't know, small things to measure the distances, like rulers, right? To measure the distances and times. And Weyl said if we like allow that gauge freedom in the matrix, we'll be able to incorporate the electromagnetism inside the general relativity. And because of that like freedom in scaling, we also have like a lot more problems basically with, for example, we will not be able to have like no absolute ideal clocks, because like the rate at which any clock measures times would depend upon its history, and it's demonstrated here by the like generalized Weyl clock paradox, which we have seen in chapter 18. But in that case you can see that depending on the path, the rate with which clock ticks, it kind of changes here. And therefore after the twin arrives back to the Earth, he can discover that his clock ticks differently from the clocks on the Earth. Yeah, and one moment.
This makes me wonder if it's gauge as in measure or determine, that they use the word gauge in this context. How to gauge something.
Yeah, it seems to me that like after you come back to the Earth, you need to gauge your clock, right? To be in sync with the clocks on the Earth. Because like as far as I remember, like gauge is the same like a calibration, right?
I'm thinking of more of it, how to gauge a situation, but the definition you're talking about, I'm not so familiar with.
Mm-hmm. Yeah, because it is translated to the Ukrainian or Russian as calibration, actually. So it's.
I wonder if it has etymology shared with gear or something.
Mm-hmm. But anyway, like from the text of the Penrose's book, it's more about like measuring something with different sticks. Like that.
Yeah, how to gauge something.
Yeah. So it's just a freedom in the scale, and that's all. And like the path dependence implied here. Okay, yeah, and basically book says that there is some structure additional to that of the null cones in that picture Weyl theory, and that structure was a bundle connection or gauge connection, and it was introduced by Weyl in order to have Maxwell's tensor as its curvature. And this curvature measures the discrepancy in the clock rates as illustrated on the picture above. Yeah, but afterwards like first of all, Einstein told that he has some objection with that because like fundamentally every particle has its frequency in terms of its rest mass, and therefore like the particle mass will depend upon its history, and also like spectral frequencies, for example, appear to be completely unaffected by an atom's history, whereas Weyl's theory would predict otherwise. So basically, there were some reasons to decline that theory in terms of like the real applications of how to say that, to the connection to the reality. But after some time passed and more like discoveries were made in quantum mechanics, for example, like people observed that they could like reuse that ideas, and instead of rescaling by any like real function here, we can use the same idea but using like a complex number of unit modulus, like a complex scaling factor here. And that's exactly what we will need in the quantum mechanics, and we will have that like gauge phase shift symmetry for the wave function there. And he says here that this non-observable replacement is still referred to today's gauge transformation, even though there is now no change in length scale involved, and the change being a rotation in the complex plane. Yeah, and in this strangely twisted form, Weyl's idea provided the appropriate physical setting for U1 connection of the kind that we have seen in the chapter 15, and it now forms the basis of the modern picture of how the electromagnetic field actually interacts. And I think that it will be more obvious for us, like that we will understand that sentence on a more higher quality level after we will first of all get acquainted with Lagrangian formulation, and afterwards we will talk about quantum mechanics, because that like interaction will actually be seen explicitly in the Lagrangian. So we will see that, and we will understand more about that connection, like interaction between electromagnetic field and wave function. Okay, and he just summarizes that the operator del that is defined above from the electromagnetic potential provides us with a U1 bundle connection on the bundle of charged quantum wave functions. And afterwards he goes to discussing the Aronow-Bohm effect, which we have already seen in the article by Jacob. And he says here that since our connection operates only at the level of quantum phenomena, we do not see this path dependence in the classical experiments. But like the main thing here is that in the region where like, okay, so let's see a setup. So setup includes like electron gun, beam splitter here, which will split the beam of the electrons into two. We have a solenoid isolated from the outer space basically, so the field is non-zero only inside that solenoid, so n is 0 for both of those beams, but like there will be some topological non-triviality in that region of space around the solenoid, and that will imply the change in the interference pattern on the screen here. And basically that means that like the electromagnetic potential is not just some kind of the passive transformation, it's not just a redundancy, it's a real thing, like existing one, and as a physical entity which could impact our beams here and change the interference pattern. Yeah, and here he says that we have like field-free region R, and that free field region is like outside the solenoid, with the solenoid like removed from the space basically. And he said that A vanishes everywhere within. He said that that region is not simply connected, because we have like a solenoid punctured out from the plane there, or a space, and the field F outside R is such that there is no gauge choice for which the potential A vanishes everywhere within R. So basically he's talking about like non-vanishing potential in R here, okay? And the presence of this non-zero potential in non-simply connected R, or more correctly the path dependence of our bundle connection in R, leads to displacement in the interference fringes and the screen. And in fact, the fringe shifting effect does not depend upon any particular local values that A might have, which it cannot, because A is not locally observable, and we can measure only the differences of the potential, but upon a certain non-local integral of A. So it's like some kind of the global, non-topological, non-trivial thing here, because we will take that integral around some topologically non-trivial loop within R. Yeah, and he said that dA vanishes within R, but the integral is unaffected if we continuously move our closed loop around within R. Okay, and from this it's clear that the non-vanishing of our integral within the field-free region, and therefore the Aronow-Bohm effect itself, depends upon this field-free region being topologically non-trivial. So, yeah, I'm not understanding that like in the like really detailed picture, but as far as I understand that, it just means that like we will have some kind of the topologically non-trivial behavior here, similar to our like spiral bundle or like bundle with curvature, right? We have seen in the chapter 15. And that,
any idea what the field free means? I'm not clear about it.
Field free, it means that we do not have any electric or magnetic field in this region where beam travel. So there are no electromagnetic field there.
Despite the solenoid.
Yeah, this turns out to be the case. Like if the solenoid is infinitely long, then there's no field outside of it, and it's a uniform field inside of it. That's just like one of the like sort of basic assumptions that that they make for this, that the solenoid is much longer than like the plane of the experiment.
So if you made it long enough, it will like puncture a line in the 3D space, right?
Yeah, it should just remove a point. You know, if it's infinitesimally, if it's got an infinitesimal radius, it should only puncture a point in the plane. So basically, the fields are uniform within the solenoid and zero outside the solenoid if it's long enough.
Okay.
Yeah, and probably it would be interesting to take a look and search for the solution for that exercise. Maybe they will explain more about that integral and the whole structure of the experiment. But I'm still thinking that to understand that better, we will still need to understand more about quantum mechanics, about wave functions and how those are changing basically. And only afterwards we'll be able to understand that experiment in like the whole, its wholeness basically, right? Yeah, and here at the end, Penrose talks about like that basically the while ideas are still living, and we can see that those like in the electromagnetic connection, and also they were also adapted for the generalization of electromagnetism, referred to as Young-Mills theories, and those are used in the description of both weak and strong interactions in modern particle physics. Yeah, and he says that like the gauge connection idea really does depend, strictly speaking, on the existence of a symmetry that is supposed to be exact and not directly observable. And he recalls that Einstein's objection to Weyl's original gauge idea was about that the mass of the particle and therefore its natural frequency is directly measurable and so cannot be used as gauge field in the sense required. And we shall be finding later that this issue becomes distinctly muddied in some modern uses of the gauge idea. Okay, so I basically made the conclusion that we need to just recall the question about the mass afterwards somewhere. So I don't know where to apply that fact he talked about here, but probably he will link us later to that paragraph. Phew. Yeah, so it seems that's all. Any questions? Let's discuss.
Not from me. Well done today.
Okay. Okay, then I will stop the recording. One moment. Wrong.